The name of this video is Infinite Charged Line. This is a very important video. Infinite Charged Line. Note that we will solve this problem in a number of different ways. This is the first way we are going to encounter in this course, which is going to be based on Coulomb's law and the superposition principle. What is the problem? The problem is that of an infinite straight line. So this line, let's sketch it here in the following fashion. It's infinite. The 3-dash line means infinite in this case. Above and below, here. This line, it's oriented, let's say, upward. Doesn't matter really much in electrostatics. This orientation will be critical in magnetostatics, which we are going to encounter later in this course. We call this line gamma. Suppose that this line is characterized by a continuous charge distribution, which is uniform. So uniform charge distribution. This corresponds to a constant density, and the density has to be linear, so lambda. Since this is an infinite structure, it is not okay to consider the charge on it typically. We consider the density, because otherwise typically you end up having an infinite charge. So we want to consider the density lambda, okay, which is linear for this straight line. This is the problem at hand. This line, suppose that is the edge here of an infinite, ideally, page that I have. So this is the edge, is the infinite line gamma, like this. We want to find the solution on one of the infinite half planes or semi-planes stemming, generating from this line gamma. And so let's pick an observation point somewhere, let's say here. This is my observation point, capital P, where I want to observe and measure the electrostatic field due to the entire line. Okay, point capital P, which is where I place my test charge as always. This is my source charge distribution, which is continuous in this case, and uniform. All right. So in order to solve this problem, as always, we need to follow the 4 steps. So the first step is to choose a proper coordinate system. Since we are looking at a half plane, I could choose a Cartesian coordinate system, but for reasons which will become more apparent later, it is desirable to use instead a cylindrical coordinate system again, where the cylindrical coordinate system will look like this. So this is the z-axis of the coordinate system, z, and this will be my r-axis. Here, the radial axis. The angle bar phi from the origin here goes in counterclockwise direction. I'm not going to discuss too much about this bar phi here. So if you want, if you look at this problem from above, so if I look at it from above, what I see something like this. So I have the trace of my line here, okay, this is my line. And then I have, so this is my line here. And then I have my coordinate system, which looks like that. This is r, this is bar phi, and this is my z, which coincides with the line itself. So that's when we look at it from above. Okay, I'm looking at the line from above and from the side in this fashion. Okay. So with this in mind, we want to find the field at this point P. So the first step is done. Coordinate system, we have chosen an O, R, bar phi, Z cylindrical coordinate system, okay, with Z axis here. The second step is to identify all the electrostatic fields which will allow us to understand a little bit what's happening with this problem. So in this case, we will come back to the symmetries of this problem later on, but because we have a translation symmetry, and again, I will have an entire video about symmetries in the near future. So we have a translation symmetry, which means if I observe this line and I translate it up and down, it looks always the same from any observation point capital P. We will come back to this, so don't worry too much about this now. Anyway, with respect to this origin O, since it's infinite and there is this symmetry, I can pick, for example, an infinitesimal charge element centered in the neighborhood of a point Q here, okay? And I can pick one which is opposite with respect to the origin O, so if the distance here from O to Q is Z, and I can choose another one at the distance minus Z below the origin, and so I'm going to have another infinitesimal element somewhere here, in the neighborhood of a point, which I call Q prime. This is one pair. This is one pair of infinite pairs of opposite charges. These charges are infinitesimal point-like charges. So this charge here, around the point Q, capital Q, is an infinitesimal point-like charge dq. Similarly down here, this will be another dq, okay? This charge dq, any of these two charges dq, is given by the uniform density lambda times the length of this axis, of this element, of this infinitesimal element, dl in general, but with respect to a cylindrical coordinate system, a dz. So, lambda dz is dq, okay? Lambda dz is dq. Now, let's consider the infinitesimal electrostatic field due to dq at point capital Q in the observation point capital P, Coulomb's law. So it has to go with the straight line here, which connects capital Q and capital P. It will be like this. Similarly, from Q prime, from capital Q prime, from Coulomb's law, we obtain this infinitesimal field. So each of these fields, let's call them, each of them, dE at point capital P, okay? These are the two d's due to two opposite charges of one of the infinite pairs of opposite charges that I can have with respect to O in the line gamma, which is characterized by lambda, okay? All right. So now we know these d's. So we found translation, in parentheses, we'll come back to this. Most importantly, we identified the d's of one pair of charges. The next step, step 3, is to identify the degrees of freedom. Okay, so if we look at this, we know that this argument can be repeated for all the infinite pairs, so it's the same. And so we note right away that the z components of these dE fields are opposite of each other for each pair, so they cancel out, whereas the R components sum up, as we have done similarly for the case of a circle. In that case, we had a circular symmetry, and so here we have an infinite straight line, which, because of these infinite pairs, results in this summation here, okay? So the only degree of freedom has to be along the r-axis, which is where the test particle can only accelerate on this axis. And note that because of the translation, as well as, and again, I put it in parentheses because we will discuss this in detail later, because of the rotation symmetry of this line, okay? Because if I look at the line from above like this and I rotate it, it doesn't look different, it looks always the same. So there are these two symmetries with this line. Because of this, if I find the solution for a point P here in one half plane, in one semi-plane, generating from the line gamma, basically I find it, this is equivalent to find it everywhere for each point P in space. I just rotate the solution everywhere, translate it up and down, and I get the same solution. All right. And again, I will come back to translation and rotation symmetries later on. Now, the next step is to actually solve this problem by means of Coulomb's law. plus the superposition principle. PR again for principle. So how do we proceed? Well, the first thing we want to do is to write down the infinitesimal field dE at point capital P due, for example, to, let's say, this charge capital Q, okay? So this one is going to be 1 divided by 4 pi epsilon naught, as always. The charge dq, we already wrote it here, so it's lambda dz. This is my charge dq, divided by this distance, which again I call Greek z, and I need to square it, Coulomb's law, Greek z square, and the direction, of course, in general is this arbitrary direction, but if I call this angle theta, which is the same as this angle here, in order to project along the r-axis, to project along r, because it's the only contribution I know I'm having here, I need to multiply times the cosine of the angle theta times ur. And so we can finally rewrite this as 1 over 4 pi epsilon naught lambda dz over d squared. What is cosine of theta? The cosine of theta is nothing but this distance, which is small r on the r-axis, divided by Greek z, r over Greek z. So we obtain lambda dz over Greek z 3 times, so cube. So lambda dz times r from the cosine, divided by z squared and another z to the cosine. So as always, z, Greek z cube along the r-axis. So let's rewrite here the infinitesimal field, electrostatic field dE at point capital P. Let's group a few things together. So this is nothing but all the constants. We can take them out. So we're going to have lambda times the direction, which is r, the radial direction, ur, divided by 4 pi epsilon naught. And then we need to have the distance r divided by Greek z cube. So this would be Greek z, let's write it down here. Greek z is nothing but the square root of r, small r square, plus z square from the Pythagorean theorem to the power of 1/2 square root. So here we have from the previous calculation, which I just erased, we're going to have small r square plus z square. Now this is z cube, so it's 3/2 as always, 3/2, because it's 1/2 power of 3, so it's 3/2. Good. So that's what we get here, and here we have r. Okay, so this is our infinitesimal field due, for example, to this point-like charge infinitesimal point capital Q, which is our source. All right, now we need to use the superposition principle in order to get the overall field, electrostatic field E at point capital P. And when we do that, these are all constants of integration. So we're going to have lambda times the direction ur divided by 4 pi epsilon naught. Then we need to integrate from minus infinite to plus infinite, because we are integrating with respect to dz, which I forgot to place here. So this is dz. So we are integrating with respect to dz. So it's in dz, where the charge is distributed from minus to plus infinite. And then we have simply the same structure here, r divided by r squared plus z squared to the power of 3/2. And the direction is already there. It's a vector. Okay, so now, this is a very important integral which you need to know how to solve, and it requires a trigonometric substitution. Okay, trigonometric substitution as follows. So we know that z over r is the tangent of theta. So z divided by r is the tangent of this angle theta, from which we find the two things we need. The first is that z is equal r tangent theta. Eventually I want to use it in here. And the derivative of z with respect to alpha, which eventually gives me dz, is nothing but r divided by cosine square theta, which is the derivative of the tangent. So these are the two quantities which I need to plug in here and use them. Now, this is the trigonometric substitution. We will need this again in this course, even when we do the finite line of charge. All right, so now that we know that, we can, first of all, substitute z into this expression in the denominator. So we have, in the denominator, we have r squared plus z squared to the power of 3/2, okay? And we need to remember that it's in the denominator, okay? So when we do that and we use this condition here, we are going to get r squared plus zeta squared, which is r squared, times the tangent of theta squared, which is nothing but the sine square of theta divided by the cosine square of theta. Okay, this is the tangent square to the power of 3/2, which again, let's remember, is in the denominator. So this is in the denominator down here. Let's not forget that. I can factor out r squared, which to the power of 3/2 is r cubed. And then I have 1 plus sine square over cosine square, which is in the denominator cosine square of theta divided by 1 is cosine square of theta divided by cosine is 1 plus sine square of theta. We know that this quantity here, it's obviously 1, and this quantity is to the power of 3/2. So we get r cubed 1 over cosine square to the power of 3/2, which is cosine cube. Okay. We also know that dz is r over cosine square, which times another r gives us E at point capital P equal lambda u r divided by 4 pi epsilon naught. Okay. So now here, let's remember that this is in the denominator. So we have the integral. Okay. Now note that this is my angle theta below. Okay. So minus infinite is down here. So when we are at minus infinite, theta is actually minus pi over 2 at minus infinite. And similarly, we plus pi over 2 at plus infinite. So we go from minus to plus pi over 2. d theta, we change it with our r over cosine squared d alpha. So we're going to have, I apologize, this is called d theta, not the alpha, it's d theta, like here. Okay, so not the alpha, d theta. So d theta, then I have r over cosine squared, but there is another r here. So it's r squared over cosine square of theta. And from this one, we have r cubed divided by cosine cube, but inverted because it's in the denominator. So it's cosine cube of theta divided by r cubed. So this and this cancel out, this and this cancel out. And so, at the end of the day, what we obtain is the integral in d theta of the cosine times 1 over r. The integral of the cosine from minus to plus pi half, it's simply 2. It's simply 2 because it's the sine, which gives me a 2. So 2 divided by 4 is 2. So I end up at the end with lambda divided by 2 pi. There is 1 r left here, 2 pi epsilon naught r, and the whole quantity times u r. So this is the electrostatic field E due to this infinite line of charge. Lambda over 2 pi epsilon naught r, u r. And I think at the end of this course, and 342, you should remember this forever and ever. What happens, discussing Piazza, what happens when, what if r goes to 0 plus? What happens in this case to E at point capital P? Please meditate about that. All right, so in this video, we consider an infinite straight line, gamma, with a uniform constant linear density, lambda. We want to find the electrostatic field at any point P in space, capital P in space, which is the same as to find it on one semi-plane, infinite semi-plane stemming from this line z. By rotation and translation is the same everywhere. We will come back to this concept again later. The coordinate system is cylindrical. The d's of a pair of the infinite opposite pair of infinitesimal point-like charges q and q prime, we found it here. This allows us to realize that actually only r can be the degree of freedom. So then, which is in fact what we find here in the final solution, which we obtain for one charge, q or q prime, by means of Coulomb's law, already projected. This is already projected along the r direction here. And eventually we need to use the superposition principle to integrate with the trigonometric substitution z over r equal tangent theta. Keep in mind that from minus to plus infinite becomes from minus to plus pi over 2, and we obtain the 1 over r dependence which we wanted. So I will see you with some more example in the next videos. Thank you.